All right, gents, where we left off at, we are talking about the fundamentals of Ethernet, right? So we left off at, we were talking about different types of pinouts, and how those pinouts lead out to be constructed different types of cables, the difference between a crossover cable and a straight through cable, right? Crossover cable, they transmit data on the same pair. Straight through cable, they transmit data on different pairs, right? And of course, little table that you guys see here, Cisco does a great job laying it out based on Ethernet and fast Ethernet. What do I mean by that? 10 base T and 100 base T. What pins are used, right? So pins 1 and 2 for transmit are typically used by PCs, routers, and wireless access points. And of course, on hubs and switches, hubs, I would hope they're not used anymore. They transmit on 3 and 6. And of course, the diagram at the bottom, figure 213, again, grabbed by the book, not my infograph. You guys can see this as well. You guys see the crossover cables are used between the switches, right? Same device or what have you. And straight through cables are used with the end users devices, right? So, and I know the example is what you will use is if you guys ever watch DC or Marvel, right? We'll use DC because of course that's my favorite, right? Batman is a superhero, right, in DC. And Superman is a superhero in DC, right? If they were switches, they would, communicate with each other using crossover. And of course, if they made a guest appearance, it would make sense because of course they're in the same universe, right? But let's say the PCs are Marvel, right? Totally different, right, universe. So for them to connect, we would have to use a straight through cable, right? Or do a major event, right, in the cinematic universe, right? So hopefully that makes sense. I'm nerding out too much. Let's go ahead and jump into the technical stuff. I know all you guys are DC fans, right, Greg? All right, so quick diagram. Of course, I know the previous page I went ahead and touched on 100 base T, 10 base T and 100 base T, right? Ethernet and fast Ethernet, right? And so now 1,000 base T, right? That's gigabit Ethernet, right? And here are the pinouts. This is how they look for this, right? Some of my old school guys and guys of recent that make their own cables, they know what this is, how those colors look, or what have you. So you can see, of course, how the wires look. 1, 2, 3, 4, 5, 6, 7, 8, right? So you guys see how that looks, okay? And of course, these are just, quick little diagrams showing you guys some of the components of fiber optic, right? You got your core, cladding, buffer, strengthener, outer jacket. And this next diagram, I think it'll help even better explain how fiber works, okay? All right, so if you guys look at the top figure, right? It's a fiber cable, okay? Like you guys saw in the previous diagram, there's a core, right? And you got your cladding, your outer jacket, sort of say, right? But all in all, there's light passing through it, right? In either of the diagrams, right? And I'll discuss the difference between the diagrams in a second, right? But that's at a super high level, what fiber is, right? It's light passing through a cable, right? Remember when I said that that's why everyone, right, in the technical space, is very peculiar about fiber. We can't bend the cables, we can't step on it or what have you, because any little bend or what have you, light won't pass through. And the fiber, the small fiberglass that we spoke about that's inside of that, it'll break, right? So we have to be very peculiar on how we handle fiber cables, right? So as you guys can see, figure 216, figure 217, two totally different figures, right? There's two different types of fiber cables, right? You have, well, I'm sorry, let me correct myself. Two different types of fiber modes, right? You got multi-mode fiber and you have single mode. All right, we'll jump into that in a second, but as you guys can see, there's a huge difference of how it's laid out, how it's built, or what have you. So you see with multi-mode, right, at a quick glance, it looks like the light is bouncing up and down throughout its core, right? Single mode, that light, right, that's transmitting data, it's passing straight through, okay? And I'll of course explain why in a second. All right. So looking at this, right? If we look at the cable type, right? Let me go ahead and get my handy dandy. No, right? Let's look at cable type real quick, right? Let me explain that first. MM, multi-mode, SM, single mode, right? What's the difference, right? Multi-mode, typically used for short distances, right? But a little bit longer than fiber, right? Fiber, I'm sorry, a little bit longer than copper, I'm sorry. So copper being what, 500 feet, right? Multi-mode can do up to 400 meters, depending on the type of cable, okay? Single mode, I mean, building to building, you know, one part of the city to one part of the city, okay? That's the big difference between multi-mode and single mode, right? And if you guys are not familiar with it, you guys are probably asking, okay, when will we use fiber cables? You guys see it every day, right? You may have, right? We may have one site, right? One site, a headquarters site, but then we may have a branch that's 2 cities away. It's connected via fiber, right? Or we may have a college campus, right? Different buildings, but it's like the buildings are miles away, connected via fiber, okay? And so how the fiber cable is built, right? And of course, when we have our in-person lab, I'll show you guys, right? So there's, you know, there's typically 2 notches, right, in a fiber cable. They're connected and slammed together, right? One is responsible for TX, right? And one is responsible for RX, right? Okay. What is TX and RX, right? TX stands for transmit, right? RX, as you guys can probably guess, stands for receive, okay? And so typically fiber cable on each ends, right? TX is going to be aligned with the receiving side, right? And vice versa. TX is going to align with the RX on the other side, okay? Simple enough. Let's keep going. Okay, right? So remember I was telling you guys about copper, or how this chapter explains unshielded twisted pair versus the different type of fibers, multi-mode and single mode, right? Cost for copper, real low, right? We can just go to Staples, wherever, get a copper cable, boom, we're done, right? Fiber cable, we gotta, you know, typically order that or what have you, because again, it's hard to come by. When I say hard to come by, I mean it's not going to be in your Office Max, right? Or your Staples or what have you, or your Best Buy, right? And so, and that's just the cabling, right? Cost of the switch port, right? Typically, access layer switches, or just switches in general, come with copper ports, right? Unless you order a specialized switch, right? The switch port, maybe you have a switch that's copper, right? And has fiber ports, right? Now you have to think about not just the cable, right? You got to think about, do I have a transceiver? Or if am I going to use a DAC cable, right? A directly attached cable that already comes with a transceiver at the end of it, right? These are things that you have to, you know, take in perspective whenever you're thinking about fiber, what have you. Again, things you need to know for the exam, right, is in this table. So screenshot it, do what you got to do. This is in your book. You will have to know the difference between copper, the use case for copper, right, and the relativeness between different topics, multi-mode and single mode, right? We went over the distance, right? So unshielded twisted pair, I gave it some grace. Unshielded twisted pair looks like here's 100 meters, right? Multi-mode, 500 meters, single mode up to 40 kilometers, okay? And, you know, some positives here, right? Unshielded twisted pair has some interference possible. Fiber, as you can see, none, right? Risk of copying, you know, data that's transmitting via the wire. Unshielded twisted pair of copper, some, it's possible. Fiber, none, right? Hope that's clear enough, right? And guys, remember what I said in the past, there's sometimes I won't be able to give you guys analogies because again, it's just, you know, the information will just be straight just be a straight shot to you guys, because again, this is what you'll need to know for the exam. Okay, this is my favorite part. This is my favorite part. Now I'm going to take my time on this slide. If I miss anything, if something doesn't make sense, please stop me. Okay, so let me get my pencil. I like my pencils. This is an Ethernet frame, right? We were talking about the OSI model and encapsulation, right? When that packet comes all the way down, right? It stops at a packet, and it needs to get onto the wire. So it gets encapsulated at layer 2, right? The data link layer, right? And so we need to put a header and a trailer on it, right? And so within that header and trailer, there's a few things, okay? In our header, we have our preamble, we have our SFD, we have our destination, we have our source, and we have our type, right? In our trailer, we have our FCS, okay? So reading it word for word, right? Line by line, we can look at what these different things mean. Preamble means synchronization, right? You don't need to know that for the exam. This is just for your own knowledge, okay? SFD, what it stands for is start frame delimiter, right? Signifies that the next byte begins with the destination MAC address field, right? What does that mean, right? So this basically is saying, let's say it's reading the frame, right? Saying, hey, just let you know what's coming up next, if you're reading this frame, is the destination MAC address, right? And of course, self-explanatory, destination MAC address, source MAC address. Destination MAC address, the recipient of the frame, who's going to go ahead and get that frame. Source MAC address, right? Who's sending it, okay? Simple enough. You guys heard me talk about that before a lot, so I'm not going to really go super in depth, right? Let's talk about type, okay? So type, let's read a description. Defines the type of protocol listed inside the frame, right? So today, most likely identifies IPv4 or IPv6, right? So even though packet tracer, and I'll show you guys this tomorrow, we're going to do our lab in packet tracer based on what I showed you guys. You are able to see the type if we look at a packet capture, right, and see if maybe it's a IPv4 packet that was encapsulated inside this frame, or it was IPv6, or if it was something else, right? Within the Ethernet header at the type section, it's going to have a hex saying the type, right? A hexadecimal value saying the type, okay? Right? And how long that value is based on this section, right? The bytes, right? Of how much it weighs, how much, it has on there, okay? Data and pad, right? Here's the bread and butter, right? This is everything that was encapsulated before it got to layer 2, okay? And so let's read the description, right? Holds data from a higher layer, typically an L3 PDU, right? Usually an IPv4, IPv6 packet. The sender adds padding to meet the minimum length requirement for this field, right? 46 bytes, all the way up to 46 bytes being the minimum, all the way up to 1500, okay? Or if I'm not mistaken, maybe a little bit less than 1500, but we'll get into that in the future, okay? And then of course, last but not least, we go to the end of the frame, right? The trailer, right? Frame check sequence, right? That's your check, right? You can think of that like TSA, right? It's making sure, hey, everything looks good. You're all right? Okay, perfect. You're good to go to get on the plane and start traveling, right? And let's read the description, as Cisco explains it. Provides a method for the receiving NIC to determine whether the frame experienced any transmission errors, right? Was it manipulated, right? Was it, does it look jargled, right? Whenever it was transmitting via the wire, right? So the FCS has plays an important role whenever transmitting frames onto the wire and sending frames from the source to its destination. Okay, simple enough. Any questions, guys? Okay, cool. I'll keep going. All right. I'm not going to read this whole thing. I'm going to go ahead and just say exactly what this is. Layer 2, how layer 2, communicates and talks with one host to another is by MAC addresses, right? That source and that destination field is going to have a MAC address, right? And so that MAC address is going to look exactly like this. Take a screenshot or what have you, right? It's going to be 12-digit hexadecimal numbers, okay? Make sense? Okay. All right. Let's keep going. There we go. Okay, cool, right? A lot of information. We're going to take our time with this, right? So let me get my pencil. This is definitely going to need a pencil. Okay, so let's look at this first figure, right? Figure 2-20, right? So again, MAC address, 12 hexadecimal letters, right? What is that in bits, right? It's 48 bits, right? Okay, so 48 bits in total, okay? 12 hex digits, right? And this is how it looks, okay? But let's take a look at the top, right? So you have your OUI, and then you have your vendor assigned, okay? What does that mean? So your OUI, right? Let's say we have, Cisco IP phones, right? And we take a look at its, MAC address or the Ethernet addresses. The first part, the first 24 bits, or this right here. Let me go ahead and clear. Let me change the color. This right here, the first part of a MAC address is always going to look the same, depending on the vendor, right? So maybe Polycom phones, their first 6 hex digits, right? First part of the MAC address, what we're going to call this, they're always going to look the same. Maybe they'll have a different model. Maybe it'll look different, but they all look the same based on that model. Okay? How it differentiates, right, is here. Is right here, the end part of it. Every time it leaves the factory, right, the vendor or the people that are creating these devices, what have you, they're going to say, okay, let's put our OUI on it, but then this device, we're going to go ahead and create a random number, right? Random values of 6 hex digits that's saying, how to identify this specific device. Okay. Because imagine if they never change that up, if we plugged all phones to the same switch that had the same OUI, right? And the same MAC address, dude, we just added more problems to our network. Okay. So that's basically how a MAC address is built, right? 12 hex digits. First part is the OUI, from the factory, the vendor, what have you, whether that be Cisco, Polycom, Juniper, etc., right? Where it's going to be different is the last part of it. Okay. Let's go ahead, clear that. Okay. Let's talk about table 2-7. And again, guys, I'm taking my time because again, this is very important stuff before we start labbing. So we gotta take care of this, take care of this first before we start labbing and start asking you guys questions. Okay. So MAC address, right? What does it stand for? Media access control, right? There is a standard, right? RFC by IEEE that identifies what MAC address is, right? Or MAC is, right? So 802.3, right? Stands for Ethernet. It defines the MAC sublayer of IEEE Ethernet, right? Please take note of that. You guys would not just need to know it about the exam, but of course in your future, right? Ethernet address, NIC address, LAN address, right? And so basically that's the address that's burned in to maybe your Ethernet port, your RJ45 port. Every port will be different. Okay. Every port will be different. So but that's what's built into each port on any device if it has an RJ45 port. Okay. Next, burned in address, right? The 6-byte address assigned by the vendor making the card, right? So again, the MAC address. Okay. Now here is where it's going to get tricky, and definitely going to take some labs for it to make sense. Okay. So 3 different type of addresses. We got unicast, broadcast, and multicast. You guys probably heard of those before. You guys probably have not. Let's go over it, right? Unicast address. Think of uni as unique, right? So unicast being unique to each device, each interface, right? So unicast address, right? It's a term for a MAC address that represents a single LAN interface, right? It's unique to each interface, okay? Right, so maybe, Nelson's PC, his Ethernet adapter or NIC card, right, on his PC has one unicast address. It's going to be different than mine, right? So we have different unicast addresses, all right? Broadcast address, right? Broadcast, I'm sure you guys heard the radio, what have you, broadcast messages, right, to everybody, right? Maybe saying, hey, there's rain coming, right? Or there's going to be an earthquake, right? That's typically what a broadcast is, right? And now let's talk about this in networking, right? Broadcast address means an address that means all devices that reside on this local area network right now, okay? And again, we'll touch on that, of course, when we, talk about broadcast domains and VLANs and what have you, but just for now, an address that means all devices that reside on this land right now. And again, going back to the example, right? If everybody in Miami, right? Let's say we all live in Miami, is receiving a message from the radio station that's saying it's going to rain at 2:00. Only people in Miami, right, can hear that broadcast. People in Orlando shouldn't be able to hear it because they're not in Miami, right? That's an example of a broadcast, okay? Multicast, right? Similar, but different, okay? So multicast address, right? On Ethernet, multicast address implies a subset of all devices currently on the Ethernet LAN, okay? Very good wordplay by Cisco. Like I told you guys before, Cisco has some wording to where it will confuse some people, okay? So with broadcast, right? Broadcast, it's going to go out to any and everybody, no matter if you're interested in the message or not, okay? And it's to everybody that resides in the local area network, right? Or in the city, if we're still using our Miami example. Multicast address, right? Multicast, right? Let's still use our radio in our Miami example. What multicast is, right? It's think of it as on demand, right? We have our regular radio where if you listen to it, you'll get this message. Think of multicast as Cyrus radio, right? You have to subscribe to hear those messages, right? That's at a high level what multicast is. And we'll touch on that. I'll make sure I touch on that in future sessions and labs, but that's the difference between broadcast and multicast. It works similarly to broadcast, right? Because it's going to send a message to everybody, right? That's what multicast is going to do, but only for people that's tuned in, that's subscribed, not to people that's not subscribed, okay? And of course, at a technical level, let me go ahead and get my pencil. As you guys can see here, right? Here's one thing I want you guys to take note of. Broadcast address, frames sent to this address should be delivered to all devices on the Ethernet LAN. It has a value of FFFF.FFFF.FFFF, okay? What does that mean, right? If it's a broadcast message being sent from a host or to, to anywhere, right? The destination MAC address, right, within that frame is always going to be FFFF. So you'll know if you see a source, maybe, from a unique individual host, and if you see the destination for all Fs, that is a broadcast message. A multicast message will not have this, okay? versus multicast, there'll be a specific value, right? It'll look like a regular MAC address, right? But it'll be specified, right? It'll be unique, right? Based on whoever wants to subscribe to that MAC address, right? Whoever wants to send messages to that MAC address, okay? And again, we'll touch on that later, but just take note of it, okay? Let's clear this up. Okay, cool. So, again, you know, basically what we just talked about, right? How that data looks, right? We see, you know, if we're talking about the type field, right? I told you guys I'm going to let you take a look at it, right? The trailer is going to have the type, right? It's going to say, oh, this is you know, with what we encapsulated in this is maybe IPv4, right? So I'm going to go ahead and set the type, right? And it's going to be a hexadecimal value, right? So IPv4, right? The type field is going to have 0800, right? Maybe the packet that's encapsulated is IPv6, different hex value, right? Right. And if it's a device that's reading, of course, this frame, it'll be able to decode and see the type and say, okay, this is IPv4, perfect, know what to do with this. IPv6, know what to do with this, right? And again, that's right here on the header, that last piece, right before that payload, right? Okay, let's keep going. Okay, as always, right? Our first, you know, first few sessions so far, we talked about source and destination, right? And so this is how it looks. We have no layer 3 instance here, right? We just have switches, right? How's that communication happening, right? We have our source, right? PC1, that's right here, okay? And we have our destination, PC2, okay? All that's gonna be in the header, okay? I know I'm repeating myself, but I wanna go ahead and make sure it sticks, right? PC1 is gonna send it up, right? Send it up to the switch. The switch is gonna go ahead and send a message and say, hey, I know where this MAC address lives. I'm gonna go ahead and send it this way, right? And we'll talk about unknown unicast, you know, messages and broadcasts, what have you, later, right? This is just fundamentally, this is how that traffic flow works at layer 2, right? Switch 1 is gonna send it. Let's say it does know where PC2's MAC address sits. Switch 2 is gonna say, okay, all right, this sits off of interface fast Ethernet 0/2. I'm gonna go ahead and send it here, okay? Simple enough, hope that makes sense, okay? Let's go ahead and clear it. There we go. All right. And this is the last part of the of today's presentation. Again, I wanted to keep it really technical. I can't give you guys a lot of analogies because again, we do have to touch on the technical piece because you guys will need to know this for the exam. Okay. So let me get my pencil. It'll help out. There we go. Okay. So 2 concepts in Ethernet, half duplex and full duplex. Okay. Half duplex, meaning the device must wait to a device, right? Must wait to send if it is currently receiving a frame. In other words, it cannot send and receive at the same time, right? And on the opposite, we have full duplex. The device does not have to wait before sending. It can send and receive at the same time. And this is in regards to data transmission at layer 2, okay? Before it gets onto the wire layer 1, okay? So what is half duplex, right? We got Larry, we have Archie, we have Bob, okay? Remember we talked about hubs, right? Very old school device, right? And typically the technology within hubs was half duplex, right? It does data transmission at half duplex. What does this mean? Okay, so Archie sends a frame, right? He wants to send it to Larry, okay, right? Sending, okay. Archie sending, right? He's not receiving anything. He can send it. Bob is sending something. He's not receiving something. They can shoot that out. That's fine. They're not receiving something at the same time, right? Larry, right, may want to go ahead and send something, right? But he's getting messages from Archie and Bob at the same time. Crash. There's a collision. Because on a half duplex network, right? It can't send and receive at the same time. It has to wait till somebody's done talking to go ahead and send that data. Okay. All right. And compared to what? Full duplex, right? Full duplex, we got Larry, we got Archie, we got Bob. Okay. Larry set up with full duplex. What does this mean? Larry can go ahead and talk to Bob all at the same time, right? They can go ahead and keep talking. It's no problem, right? All good. But Bob wants to talk to Archie. Bob is sending data, right? And Bob is talking to Archie, right? But Archie can't talk back to Bob until Bob is finished. Okay. And so if you guys can even think about that, right? Let's say if that's how it was right now, right? We would be in the Stone Age, right? Data wouldn't go as fast as it does today. Okay. And so in today's world, right, most of our Ethernet technologies and topologies that are set up and networks that are set up are running in full duplex, right? If it's running in half duplex, there is a specific reason, right? And there are good use cases. I won't jump into that just now. But again, typically it's in full duplex, so it can send and receive at the same time, right? Take note of this word collision, right? And take note of this word, it's not on here, but broadcast, right? We're going to talk about collision domain and broadcast domain in the future, okay? All right, and you know what? We can talk about collision now, right? I think that'll help this discussion, right? With this hub, right, there's no separation. There's no separation, right? So it's one big collision domain, right? They all have to talk at the same time. There's no separation, nothing. So it's damn near their wires are connected to each other, right? That's in a half duplex setup, right? They're all in the same collision domain, right? Well, somebody back in the day, they went and say, hey, what if we can create a technology, right? Create something that's better than a hub, right? That can make it to where we can have individual collision domains on each port, right? What will that enable us to do? That'll enable us and of course devices to send and receive data at the same time, right? So on hubs, right, it's one big collision domain. On a switch, each port is its own collision domain, right? Each port is its own collision domain, so it can send and receive at the same time, right? And so even though each port, right, we'll take it a step further, is its own collision domain, right? And they can send and receive at the same time. Does that mean they can still talk to each other, right? In general, yes, right? Because they're part of the same broadcast domain, right? We don't have no delimiters of VLANs or ports or what have you. By default, right? Everything connected, they're part of the same broadcast domain, right? But each individual ports on a switch, right, is its own collision domain, right? Hub, entire collision domain, right? So right here is one big collision domain. Okay? Hopefully that makes sense. Okay? And again, that sums up That sums up layer 2. That sums up layer 2 at a fundamental level. Now we're going to dive deep a little bit more, right? Talking about the different protocols at layer 2. But again, this is fundamentally, right? We're talking about how a frame looks, right? The header and trailer, how the communication happens. And again, we're going to dive a little bit deeper. So we, start to learn and see how the switches help with the data transmission and communication or what have you, and encapsulation. Okay. Any questions so far? All right, guys. Well, this sums up today's session. Again, tomorrow is going to be a fun lab. We're going to go over the labs that I sent out to you guys early this week. If you haven't received it, please ping me directly. I'll go ahead and send it. And you guys have a great day and happy Friday Eve.
Thanks, David.
Thank you, sir.
Thanks, David.